So it's not going to be quite as interesting and delicious as the related rates, because for the most part, our equations are going to be straightforward. There are two parts of the maximization formulas that you need. You have the constraint. So you're going to have one equation that's going to be the constraint, and that is the equation that must be met. In this case, I have all negative non-real numbers between 0 and y, numbers x and y, that are between 0 and 20. So that when I add them together, it equals 20. So that is our constraint. That has to be satisfied. Then the other part that I'm looking for is which pairs of numbers have the largest product. That is called the objective. So the one that I'm going to max or min is going to be the objective function, and the other one is going to be the constraint. It's the thing that has to be satisfied. So I'm just going to say I've got this p, because it's not area, it kind of is kind of like area. I've got this p, let x times y equal p. And then I solve for one of the other two equations, one of the two variables in the other equation, and plug that in so I can make it a function. Now I chose to make it a function of x because that's what we're familiar with. So basically this is really, 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 really similar to when we had that whole corral thing. Remember? Back in pre-calc 1, when you asked to build a corral that had the maximum area and you had a total length of fencing of 20 yards or something. Do you remember those? Some I got some yeses and I've got some no's. So basically that's what these are, right? We didn't call them the constraint and the objective. We just said, hey, we have this corral that we need to build. This is the amount of fencing we have. What's the biggest area that we can make with that fencing? So that's similar to what we're doing now. The good thing is, though, is that we now take the derivative of it rather than doing our negative b over 2a. So back when we learned it in pre-calc 1, we would have had the vertex. Well, because we know derivatives, we can find the vertex by doing the first derivative and setting it equal to 0. Now, if it's not a quadratic, it's still going to hold true. I'm going to find my maxima and my minima. Okay? So in pre-calc 1, it was only quadratics. Well, in pre-calc or in calculus, it's not going to necessarily be quadratics. But we're going to do the same kind of thing. Typically, I'm going to have two equations. I'm going to solve for one variable and put it into the other and do derivatives of it. Questions so far? So this is not nearly as delicious as related rates. Not nearly as delicious. Dallas is like, yes, the related rates were like the best ever. So when you are trying to decide how to do these, you first have to, if you can, draw a picture, because pictures do help. You need to determine which one of the variables, if you have more than one, is going to be maximized or minimized. Then we start writing formulas. Typically, you're going to have two formulas, one that you need to be satisfied, and then one in which you don't, that you're going to use to find your maxima or minima. Also think about what your domains are on these, because these are application problems, so you're not obviously going to get, if you have an application problem and you're talking about area or perimeter, if you get answers that are negative, then you're going to toss those answers because it makes no sense in terms of your domain. So then you locate the maxima or minima by doing our derivatives and then putting those values into the original equation again. So these are not nearly as delicious. Take a look at this one. This is one that you would have seen initially back in pre-calculus 1. And Ranger has 400 feet of fencing for construction of a large rectangular corral. One side of the corral will be formed by the barn, and then the three smaller but equal rectangles will be built. We want to maximize the total area enclosed. So we would have said, I know that my x plus y has to equal 400. Notice I drew a picture. I like to draw pictures because it makes it easier for me to visualize it, because I'm a visual learner. I need to know what that translates from the English into what they're actually asking me to do. And I guess that's because I'm a recovering engineer. I don't know. I have to visualize it, or I'm just like, I don't know what's going on. So I drew my barn in such a way that I chose this entire side here to be y. Now, I didn't have to do that. I could have had individual ones being y. So all it would have done is changed it to the constraint would have just been 4x plus 3y is equal to 400. That's about all it really would have done in terms of the constraint function. But remember, we want to make this as easy as possible. So it is unlikely I would have wrote it like that. So let's get rid of that.
How did you get cy?
So if I would have drawn it instead of each individual, instead of having the entire side here of being y, if I would have said I want this to be y, and this to be y, and this to be y, I would have had to have my fencing or my perimeter amount to be 4x plus 3y. So I can do it that way. It's not wrong to do it that way, but I don't want to work that hard. So I just said that's why. Because what I want to do is I want to maximize the area. Because I want to maximize the area, my area is going to be equal to x multiplied by y. Now, if I would have made each one of those individually as y, then my area formula, first of all, my constraint would have been 4x plus 3y is equal to 400. And then my area, instead of just being x times y, it would have been x times 3 of those y's. So that's how come I'm just going to use y for the one side instead of individual y's. It's okay to do individual y's, it's just more work. Because I want to maximize the entire area. So if I'm maximizing the entire area and I'm using these y's right here, then I need to have the total of that side, which is 3y, multiplied by that x. Not a fan myself. So I would not use this one, and I would not use this one. I would have used those two. So just like before in pre-calc 1, I would have said, now I have two equations and two unknowns. Let's solve for one and substitute into the other. So I would have taken this equation right here and said, okay, let's rewrite this as y is equal to 400 minus 4x. So I have one equation solved for y. That means I'm going to take that and substitute it into the other equation. So wherever I see y here, I'm going to replace it with this information. And that allows me to write this as a of x, so it's a function of x only, is equal to x, and then 400 minus 4x. So then I just multiply through and take the derivative, so a of x is equal to 400x minus 4x squared. And now I'm just going to take the derivative of it. Now if I was in pre-calc 1, I would have found the vertex by negative b over 2a. So I'm not in pre-calc 1, that means I can do a prime of x is equal to 400 minus 8x, and I just solve for x now. I say take that derivative and set it equal to 0 because of maxima or minima. This is my critical point. Set this equal to 0 is my critical point, and so I've got 400 minus 8x is equal to 0. 400 is equal to 8x, and I get my calculator out, and what is 400 divided by 8?
50.
So I have 50 is equal to x. So if I let each one of those x's equal 50, then that's going to give me my maximum area. So now I also have to figure out what y is, because I think they want the dimensions of the individual corral or maybe the entire corral. So I need to find my y, and the way in which I do that is I take this number and plug it in right here, and that's going to tell me what my y is. So to find my y, I have y is equal to 400 minus 4 times 50. So the dimensions of my corral is going to be 50 feet by, and I'm just doing the entire dimensions, I'm not doing the individual. So the entire corral is going to be 50 feet, and that's not a multiplication, that is by. So 50 feet by, what is it, 200? Is that right? So that is the entire corral. How would I find the dimensions of one corral then? So I got 200 because I took my 50 and put it into that equation above where I just boxed the blue. And then the blue is going to tell me how I got that 200. So that is the dimensions for the entire corral, though. If I wanted an individual corral, what would be the dimensions of the individual corral? 200 divided by 3, whatever that is. So that I now know that the entire corral system will be 50 by 200, but each individual corral will be 50 feet by, what is it? 50, 56 and a, 66 and a, so 66 and 2/3 of a foot. So that's how big each individual corral would be. Now, if I wanted to know the maximum area that I can enclose, then all I have to do is go here and multiply those two numbers. Or the other way I can do it is I would have done A of 50, and that would have given my maximum area. Either one of those would have worked. Okay? So with these, they're not as interesting or delicious as the related rates, because I think these are a little bit more straightforward. Okay. Okay. Some things to think about. Why do you have to find the maximums? Well, because that's what you're trying to do. Do you need to check the signs of the derivatives around the critical points? So we found the critical points. Do I need to check to see on either side of that critical point? Do I need to check the sign of it? So say I ended up with 3 critical points. Do I need to check the sign around them to determine anything about them? I do. I should check around either side of my critical point to determine whether or not it's increasing or decreasing on either side. So I know whether or not that critical point is a maxima or a minima. So I always should check that. In this case, it was a quadratic, so I really only had one choice, and it is a maxima simply because it's an upside down quadratic. But if I did not know that, then I do need to check the signs. What about the endpoints? Would it have made any sense for me to check the endpoints of 0 and no? Because my domain for this here, if I come back here, my domain is the largest my x can be, obviously is not going to be 100. If I let my x equal 100, would that make any sense? And the answer is no, because then I just have a straight line. I can't corral anything with a straight line. I don't know if you've ever spent any time with animals, but you put a straight line out there, eventually they're going to go around that. It's true. And would it have made sense for it to be 0? No, wouldn't have made sense for it to be 0, because if you put a pole out there, that's not going to keep anything in. I promise you that. And I haven't even spent that much time on a farm lately, so I could promise you that, though. So you do need to worry about endpoints if you're not doing optimization, because endpoints make no sense in our optimizations. Okay? So true or false? I like true or false questions. For every continuous non-constant function on a closed finite domain, there must be at least one x that maximizes or minimizes. True or false? True or false? How many of y'all think false? How many of y'all think true? How many are like, please tell me the answer?
False.
If it's a closed interval, then we are guaranteed one place in which we have a maximum or a minimum. For every continuous nonlinear function, you can find the value x that maximizes a function. True or false? Continuous nonlinear function, you can find the value x that maximizes the function. True or false? How many of you say true? How many of y'all say false? How many are like, please just give me the answer? I love the honesty. So nonlinear function in which you maximize the function. How about this? Nonlinear. And I'll be able to maximize in there? Am I going to be able to minimize in there? The best I can do is find a critical point. And it, in this case, is not going to give me anything. It's inconclusive. So horizontal slide there. So the answer is false. Okay, look, it's all we have left is doing these lovely applications. So I want you all to try some of these first ones right out here. Of all rectangles with the perimeter of 10, which one has the maximum area? So let's start with the constraint equation. So I have a perimeter of 10. What do you all want to use for variables? X and Y, because you're all just going out of control. So X, I'll make that Y, this is X. My constraint function. What has to happen on my constraint function? So how do I find the perimeter of any rectangle?
2x plus 4.
So my constraint function is 2x plus 2y has to equal 10. That is my constraint. That has to be held up and true. What is the actual thing I'm going to maximize? Area. So what's my formula for an area for a rectangle?
A plus x minus y.
Okay. So go ahead and do A, B, and C. So for A, these are our two equations. This is the constraint, and this is the one we want to maximize. Always have a constraint and the one we want to maximize or minimize. So I'm going to take this constraint and solve for x or y. What do you want to solve for? Y. So y is equal to, and it's going to be 5 minus x. So I bring the 2x to the other side and divide everything by 2. So how are we so far? Okay, now I'm going to plug that into my other equation, because that's the one I want to maximize. And so I've got a of x is equal to x 5 minus x. Remember, the one I am maximizing is the one I'm going to take the derivative of. So then I multiply everything through and I get 5x minus x squared. I'm going to take the derivative, and when I do that, what do I get? So I'm going to set this equal to 0 and I solve. When I set this equal to 0 and I solve, I've got x is equal to 5 over 2, or 2.5. Okay, how are we doing? So they want to know for this one, which one has the maximum area. Well, the one that's going to have a maximum area is the one that's going to be a square. And the reason it's going to be a square is because if x is equal to 5 over 2, then I put that back into this equation right here to figure out what y is equal to. So if I figure out what y is equal to, then it's going to be y is equal to 5 minus 2.5. So y is also equal to 2.5. So you have shown what you knew in pre-calc 1, you knew intuitively by pre-calc 1, that if you're trying to maximize something, it's a square that's going to give you the maximum area if I didn't have like the corral, because the corral was not just an x and a y, it was 4 x's and a y. So if you have just an x and a y, the area that's going to be maximized is going to be a square. Now if we take a look at this next one, my constraint is not the perimeter. My constraint on the next one is x is equal to, or a is equal to xy. This is my constraint. That is my constraint. That is not the one I'm going to maximize. So the one I'm going to maximize is my perimeter, which is 2x plus 2y. That's the one I'm going to maximize. So because they're telling me it's a fixed area, a is going to be like a constant, okay? So they're telling me this part right here, it has some fixed area. That tells me that a is a constant. So in a moment, when I solve for x or y, you get to choose, I'm going to get either a over x or a over y. So when I do the derivative of it, it is just going to be a constant. It's not going to be a dA dy or dA dx. It's not going to be anything like that. It's just a constant. So which one do you all want to solve for, x or y? So let's solve for y. So again, we solve for my constraint one. So I have a over x is equal to y. That is the constraint. Now I'm going to put it in the one I want to either maximize or minimize. So then I'm going to take this equation right here and replace my y with a over x, and then I have a function in only x. Okay, so how are we doing so far? Now we're going to do the derivative of that. So let me just move this over and erase this part. So go ahead and do the derivative of that, set it equal to 0, and tell me what you all get. No, because it's just going to be a constant, so it won't matter. So I'm going to rewrite this as 2x plus 2a x raised to the negative 1. Makes my derivatives a little bit easier. So when I do the derivative, p prime of x, what did you all get? P prime of x is equal to what? 2 minus 2a x raised to the negative 2, is that right? Yeah? Okay. Now we set this thing equal to 0. So 2 minus 2a x raised to the negative 2 is equal to 0. What I really have, though, is 2 minus 2a over x squared is equal to 0. So I need to get rid of the x squared out of that denominator. How do I do that? Multiply everything by x squared. And so I get 2x squared minus 2a is equal to 0. So you'd ask me about the whole constant thing. Well, I can divide everything by 2 right now. So right now if I divide everything by 2, it shook itself out in terms of the constant. So I get x squared minus a is equal to 0. So I bring a to the other side and I solve. And so when x is equal to the square root of a is my answer. So if x is equal to the square root of a, then I go back to my constraint back up here. And so I replace, my constraint was a over x is equal to y. I put this information in right here so that I can solve for y. A over the square root of a is equal to y, and I'm totally fine if you leave it like that. Now if you want to rationalize it, you can, but I'm totally okay if you write it as a over the square root of a, which is going to be your y. That is going to minimize your perimeter. How was that? Could you imagine trying to do this in pre-calc 1? No, it'd make us cry a little bit. Okay, let's look at an actual application of this stuff, because if we don't look at applications, why the heck are we learning this? Oh, it's cool, but yeah. Suppose an airline policy states, and this is pretty straightforward, happens all the time, that all the baggage must be shaped with a sum length of width and height not exceeding 108 inches. What are the dimensions and the volume of the of a square-based box, that's important, with the greatest volume that will minimize the cost of materials? Square-based box. So the first thing I'm going to do is I'm going to draw a picture, because I'm so good at drawing. What I know is that the base, I'm going to call it x, is square. So the base has the same length and the same width. I also know that the height, we can call it y or we can call it h. It doesn't really matter what you call it. You can call them all b's if you like, instead of x's. X's and y's are okay. What is my constraint equation? What do they all have to do? They all have to have a volume, or they all have to have a sum? What am I doing with this information? They all have to add up to 180. That is my constraint equation. So I have 2 x's plus a y all have to add up to 108 inches. That is my constraint. Yes?
Why isn't it like 6x or like y? Why is it only 2x plus y? What about the other side?
The sum of the length, width, and height. So the length, the width, and the height. I've got some head shaking. I still have some nose.
They're not asking for the blue of the box, 36 then. Okay, yeah.
We cool?
Yeah.
What is it that I'm trying to maximize or minimize? The volume. How do I find the volume of a box? Length times width times height. Okay? Remember, this is my constraint, and this is what I need to minimize or maximize. Yes?
Why are the length and width the same?
Oh, because it says, and this is important, a square
Oh, okay.
based, yeah, because otherwise we would have had a third variable and we would have had to cry a little bit. And so most of all of these will be in 2 variables. Now what do I do? Solve for y in my constraint. I always take my constraint and I solve for one of the variables. So I get y is equal to 108 minus 2x. Then what do I do with that information?
Put that y into your
I'm going to plug that into my volume. And so I've got v is equal to x squared, 108 minus 2x. So v is equal to 108x squared minus 2x to the third. Now it's in terms of x. Now what do I do with that information? Take the derivative. So let's go ahead and take the derivative, and so I get v prime of x is equal to 216x minus 6x squared. Now what? Set it equal to 0. Then what?
Factor in x.
I'm going to factor a 6x, I hope. Does 6 divide 216?
36.
Does it? Cool. We like that. So we get 6x is going to factor out, leaving me 36 minus x here is equal to 0. So I get x is equal to 0 and x is equal to 36. So does 0 make any sense? No, because if it's 0, then I just have a piece of paper. Here, ship this piece of paper. You're going to look at me like, what? So my x is 36. How do I find the other dimensions? Plug it in. And so I'm going to plug it into where? So I'm going to plug it into my constraint in which it is already solved for. Now, I really should be checking whether or not this is truly a maxima or truly a minima. You really should be checking these to make sure these are truly maxima and minimas. But I'm just going to tell you that they are for right now, but you really should be checking this. How do I check them? I look at the sign of the derivative on each side.
Oh, okay.
So here's our last one we're going to do is 2 poles are connected by a wire. These are called guy wires that are also connected to the ground. The whole purpose of guy wires, the only reason I know this is because my last job was designing this stuff structurally, is to make sure the pole doesn't fall over. That's what the purpose is. So we have 2 wires that are connected to the ground. The first pole is 20 feet tall. The second pole is 10 feet tall. There's a distance of 30 feet between the 2 poles. Where should the wire be anchored to the ground to minimize the amount of wire needed? So the first thing I have to do is figure out what my constraint is. What is my constraint on this one? Well, what is my thing what is the equation I want to minimize or maximize?
Distance anchored to the ground.
So I want to minimize or maximize the length, right? The length of the wire needed. So where should the wire be anchored to minimize the amount of wire needed? So I want to minimize the amount of wire needed. So I need to minimize this thing plus this thing. Those are the two things I need. When I add them together, that's the amount I need to minimize. So how do I figure out that? How would I do that? That's a Pythagorean theorem. So let's call this, what do you all want to call this? So we'll call that C. So I know that that is going to be equal to 10 squared plus x squared. Do you all agree that is 10 squared plus x squared? Oh, c squared, thank you. And then what about this one? So we'll call this c sub 2, call this one c sub 1 squared is equal to 20 squared, and then plus I have 30 minus x squared. What I want to do is I want this length, I'll call it x, is equal to c sub 1 plus c sub 2. That's what I want to minimize. That's what I want to minimize. So I actually end up with two constraints. I have this first constraint and I have this second constraint. Now what do I do? I'm almost out of time. What do I do now? I'm going to take the square root of both sides of c, and then I'm going to put those in right here in all of its glory. So I'm going to take this and solve for c. So c is equal to the square root of 10 squared plus x squared. I'm going to replace it right there. And then c squared here becomes c is equal to the square root of 20 squared plus 30 minus x, the quantity squared, and that's going to go in right there. And then I'm going to take the derivative of that glorious thing. Have a great day.